So thank you all for joining this webinar hosted by Together AI, a deep dive into NVIDIA Blackwell. I'm really pleased to have Dylan Patel, the founder, CEO, and chief analyst of SemiAnalysis. Dylan, thank you for joining.
Thank you for having me.
So just to start with a baseline, is at this point Blackwell's been out in volume for a few quarters, but if you were somebody that was an AI engineer and you're using AI infrastructure, but you'd never heard of Blackwell before, what are the most salient architectural differences of Blackwell compared to previous generations, and what are the big so what implications for today's AI workloads?
Oh, interesting. So the most relevant aspect about Blackwell is performance, of course, and cost. And so while cost is only up, call it 50% or 60 or 70% versus Hopper, the performance is well north of 2x, right? So it's a no-brainer to use Blackwell if you need to use GPUs. Now, architecturally, the advancements on Blackwell vary, based on both system architecture and microarchitecture. So when we're talking about microarchitecture, for most folks that are just using, PyTorch, using cuDNN, using VLLM, using SGLang, TensorRT-LM, these sorts of, they're not worried too much about the architecture. They actually can just, run whatever PyTorch code they are and get the performance benefit without having to redo much. The folks that need to redo a lot, right, are the ones drilling way down lower level, right? Like people at Together who are doing, tensor, TKC. There's a lot more major changes on the programming model with regards to if you want to get full utilization, how you bring memory in and out of the GPU versus the compute, right? And this is something that's been happening with each NVIDIA generation. Is initially it was just a pure you issue instructions and you work on a lot of data, right? And then it started being, hey, if I want to get full utilization of the GPU, actually, I should overlap when I'm doing a computation on tensor cores and then when I'm bringing data into the two next to the tensor core, whether it's the shared memory or registers, right? And so this is sort of like two operations, right? Now with Blackwell, there's actually even a third tier of memory, which is memory within the tensor core. And it's not as simple as, hey, you just have three different things popping around. Actually, you may be ping-ponging, you may be like overlapping. It's quite a challenging programming model for those who want to get all the new performance out. But if you do, then you get not just the typical 2 or 3x on a general workload, but you're actually getting way more. And that's where, it pays to have, either your own in-house kernel folks or, utilizing something like TKC from Together, right?
Speaking of which, yeah, when you think about, so there's the rate at which Blackwell gets deployed into data centers and fleets everywhere, but then there's this sort of tail that comes after it, which is all of the future performance and efficiency gains from software optimizations. So when you think about that, like that tail, like how long do you guess that tail is in terms of like how long we'll keep seeing gains? And if you think about like layers of the stack, do you have an opinion about where you think the highest payoff is in terms of where those gains are going to come from on the software side?
Yeah. So when we look at the performance scaling of Blackwell, we've already seen significant performance improvements from software over time, right? Even Hopper alone has had some pretty significant performance improvements over time. When we talk about, hey, from January of 2024 to December of 2024, right? And note, Hopper was released, in volume in 2023. Even Hopper in January 24 to December 2024, you still had like a 30%, 40% performance improvement. And likewise for Blackwell, you've seen a similar sort of improvement, right? Even over just a few months from May to now, you've seen performance improve quite a bit in some cases, right? It's double, right? And so when we talk about performance improvements from now until the end of the year and the years after, it's hard to say exactly where, but I see another 50% to doubling in the cards, just from the fact that there is so much low-hanging fruit or performance left on the table if you are using the general open libraries, right? Whether it's cuDNN, VLM, SGLang, all these other things, these sorts of open software where you're not going in and programming the tensor core directly, right? Now, the flip side is, hey, actually today, it took some time for Tree and the rest of Together to work on Flash Attention 4, but Flash Attention 4 is already at the roofline. But using Flash Attention 4 in its beta state, it's not quite, everyone can quite do that yet. So it's going to take time for these optimizations to proliferate across the ecosystem as everyone gets used to using the hardware. And so, for the general purpose user, yeah, you're going to have another doubling of performance potentially on the tables over the next year. And even today, it's still better. It still makes sense to use Blackwell over Hopper in terms of the performance increases more than the cost increase. So buying a long-term contract on Blackwell, you're going to get a lot more performance over time.
So there's a couple good topics actually that you raise, even with what you mentioned there. This last bit around the commitment to Blackwell. So if you compare the rollout of Blackwell with, let's say, the rollout of Hopper, I'd be curious, like, what you see as the similarities and differences, both on the supply side and the demand side, in terms of, like, if you could, like, time align the Hopper rollout versus the Blackwell rollout, like what you feel like is the same or different as far as supply and demand. And there's kind of a connected question to that, which is there's this sort of longstanding tension in the industry between low pricing and flexibility. And typically, the longer folks commit, the lower the pricing gets. But then at the loss of optionality. And so I'm curious, when you think about this rollout and this kind of state of supply and demand, what strategies you're seeing companies take as far as their commitments go? Are they more or less than they used to be, and why?
Yeah, so I would say, taking the second question first, right? The commitments on Hopper at this point, everyone's just going short term because the supply of Hopper is pretty bountiful. No one's deploying any more new Hopper, right? It's mostly what's out there, and whatever's rolling off books, contracts gets put into the market, and people are doing shorter term contracts, whether that's a year, 6 months, that tends to, or it could be even shorter term than that or longer term, but generally that's the range. Whereas Blackwell's super in short supply, right? There's only so much Blackwell to go around, and this capacity is coveted because it's already higher performance TCO, right? The cost to rent it is already lower, or the performance you get out of each dollar you spend on Blackwell is already better than what you get on Hopper, and so everyone wants it, and the only way to really get it is to do these long-term contracts, right? And furthermore, because there's a lot of sort of, I wouldn't say uncertainty, but you don't know how much more performance gains are going to come, from software. So there's a lot of upside left on the table in addition to that. So it kind of gives a little bit of a challenge to folks wanting to commit, because they're like, oh, here's the performance I get today. Even if I commit, will it be 50% higher? Will it be 2x higher? Will it be 3x higher? Right? There's a lot of uncertainty there in terms of a year or two from now when software's really mature for Blackwell. And so when you contrast this with the Hopper deployments, there's a couple major differences and similarities, right? So Hopper was, especially in 2023, when it started being deployed, there were some really large clusters that were deployed by folks like Tesla and others who, they wanted to be the first cluster with Hopper, and then they ended up with a lot of challenges, right? Hey, any new chip, especially accelerated computing, is going to have challenges. So, whether it's overheating or PCIe, GPUs falling off the PCIe bus or whatever it is, failure rates being high initially. This was a challenge upfront, right? And so with Hopper, it eventually got very mature, and that made it stable. But for Blackwell, right, there's two platforms now, right? So there's B200 and there's GB200. NVIDIA, learning from the issues on Hopper, with Blackwell, they actually doubled the time for system level test, right? So the amount of time they test it before shipping it out the door is actually double, gen on gen, roughly. And so what this means is that for Blackwell regular B200, the ramp has been much more smooth. Now, of course, there's going to be learning pains, there's going to be challenges and such, but out of the gate, the ramp is actually much cleaner for B200 versus H100. Now, that's great for a lot of users, but what I didn't talk about on Blackwell earlier is that the GB200 is where you have even more interesting changes. So the microarchitecture is the same, but the system architecture is way different, right? First of all, you have ARM CPUs, which not all the software, not all the dependencies that you may use are updated for Grace Blackwell, right? They're only available for x86 with Blackwell. So the CPU architecture difference took some time to build on. People had to recompile stuff. People had to check into all the various dependencies they call in their training code and make sure everything works. That was one. That was more of a software challenge. I think most of that is behind us now, except for maybe really esoteric libraries. But for the most part, that's mostly behind. There are still a lot of learning curves in terms of feeding Blackwell with Grace versus feeding Hopper with x86 or feeding Blackwell with x86. But that's mostly behind, right? The other challenge with GB200 is they've made this amazing innovation in terms of system architecture, right? NVLink used to be 8 GPUs. Now you have 72 GPUs. And if you go look at the rack, right, it's completely different, right? It's liquid cooled. It's an entire rack that consumes 140 kilowatts, whereas H100 servers consumed 10 kilowatts. And you might put 2, you might put 4 in a rack, right? And it was air cooled. It was so much easier to deploy than Blackwell. And because there were only 8 GPUs in the NVLink domain, that made it much easier to deploy and keep track of the reliability, etc. But the flip side is you lose a lot of performance, right? Relative to Blackwell with its GB200 with 72 GPUs in one domain, you can now run really large models with all sorts of different inference techniques, all sorts of different reinforcement learning techniques, all sorts of different training techniques that you previously couldn't on 8 GPU HGX NVL8 systems, right? With Hopper or B200. So GB200 has got even larger performance gains than B200, which is what I was referring to earlier when I was talking about, hey, 2, 3, 4x, right? GB200 potentially, if you use all these new techniques, can have huge gains in performance, but that comes at a challenge, right? If the reliability of each GPU is the same, then when a single GPU fails in 72 GPUs, you have a much higher chance of of something failing, right? 1 out of 72 versus 1 out of 20, but each of the 1 will fail just as often as 1 of the 8, right? So this introduces a huge challenge, right? Furthermore, you have this massive backplane, right? So before, the 8 GPUs connected over one massive motherboard called the baseboard or the UBB, right? Now you have all 72 GPUs connecting over all of these copper wires that then go to different boards, right? So it's like a very different way of connecting everything together, and that also introduces challenges. Now, many of these challenges have been worked through or are being worked through, and the reliability has gone way up since the beginning of Blackwell, right? In the beginning of Blackwell, it was truly extremely challenging to even run anything for GB200. Now we've gotten a lot better. People are putting out software. People are running production inference, right? Publicly, OpenAI has said they're running production inference on GB200 a couple months ago, in fact, right? And there's many others who are now running production systems on GB200, but you do have to be cognizant of this, right? Hey, your workload has to be cognizant of, well, maybe not all 72 GPUs work all the time, but even with 64, it's still way better performance per dollar than just a regular B200 if you have the sophistication to do this. Right. And so this is the major challenge in contrast, right? This is a whole new set of tooling, right? Hey, how do I deal with running software that, doesn't always expect all 72 GPUs to be up, right? Maybe I only expect 64 GPUs to be up, and then I need to figure out how do I orchestrate some other workload on the other 8 GPUs. And if something in the 64 breaks down, I immediately hot swap in some of the pool of 8, and now my workload that was on the 8 maybe only runs on 4. Right? And so you have to have this high priority workload, low priority workload difference and skewing. And some companies, what they're doing is, they're running, hey, on 64 GPUs, I'm running big models like Kimi and DeepSeek and, et cetera, right? And then on the remaining pool of 4 or 8 GPUs, maybe I'm running evals, or maybe I'm running some open source model that's like a GPT OSSS or a Qwen 8B or a Qwen 30B, right? Like, you run one of these smaller models that is single GPU. So when a GPU fails, you just, you kind of rip that one GPU out and that's it, right? And then if you need that GPU in the large priority workload, you rip that work stream off and you swap it in. And so there's companies that are doing that. Together has a program to do this, and companies like OpenAI have programs to do this. So it's something that requires a lot more sophistication. Otherwise, you're only running on a fewer set of the GPUs. But once you figure that out, you have so much higher performance because the NVLink domain extends across 64 or 72 GPUs, and you can bring in all these amazing inference techniques.
Super interesting. Talking about these changes in the system architecture, and you mentioned one example of just the power per rack, which has been going up over time for a while now. And many have said that these newer systems architectures, it's not clear that the data centers that were built, let's say, certainly a decade ago, but I'm curious to get your timeline, would be able to accommodate. And I'm curious, when you think about at this point, what's depreciating faster at this point, the physical data center or the system? Or are those timelines the same now as they used to be? And kind of one other follow-on connection to that is, what is the prognosis for all the data centers that have been built more than 5 years ago if they're not necessarily going to be Grace Blackwell compatible?
So watching the history of data centers has been fun, right? So sort of, it used to be a decade ago, each rack would be 10 kilowatt hours, 10 kilowatts, right, for a single rack. I talked about how a single server of Hopper was 10 kilowatts, right? So when we got to Hopper, especially when there was so much incredible demand, people were like, any data center capacity, let's put it in there. What they would often do is they would skip rows, right? You would say, hey, this entire row, we're not going to put anything in it. This next row, we're going to put it in there, right? Oh, okay. All of a sudden, instead of having a 10 kilowatt rack, we have a 20 kilowatt rack. And so the worst data centers would have 2 GPU servers in an entire rack, right? And so roughly 60-70% of that GPU, that rack would be empty space, because there would only be 2 servers in there. You could actually fit like 8 servers in a rack if you wanted to, but almost no one can do that because no data center was designed for it. Some of the hyperscalers, they were forward-looking, right? And some data centers, right? Operators, their racks were designed and their data centers were designed for 40 kilowatt hours a rack, 20 to 40 kilowatts a rack, sorry. And so this sort of meant that they could fit 2 to 4 servers without skipping rows, and even then they'd still have a lot of empty space in the rack. But at least this was fine. But as we got to Blackwell, right, especially GB200, if you have 140 kilowatts in a rack, there was no amount of like, hey, you skip a row, all of a sudden you can fit it. You actually have to have a lot more empty space, right? You may skip entire racks, right? You might skip a rack and a row. So then you have 20, so anyways, you might do all these things to get a single GB200 in there, but then that doesn't even contemplate, well, what do I do for water cooling, right?
Yeah,
how do I cool the water?
There's cooling. Were there any other, besides power and cooling, are there other systems architecture differences that have implications for the data center?
Yeah, so on the cooling side, how do I get water there? So there are data centers where like they were even liquid cooling ready, right? And it's like, oh, okay, wow, you had a liquid cooling ready data center, and then you start specking out the data center, and the pipes are running on the roof, right? Because you're walking on the floor is a concrete slab, so the pipes and fiber and everything runs on the roof. But the data center was spec'd for cooling maybe 20 kilowatts per rack with liquid, and now all of a sudden I need to take like much larger pipes, and then, oh crap, the roof doesn't support all of the weight of the water, and so I need to add support beams for the water pipes. And so there's all these like crazy things that are happening to support a data center for the cooling, right? So on the power side, you basically just add a bunch of empty space in the data center, or you just leave a bunch of empty space and you aggregate the power tighter and tighter together. But then the cooling, the CRHs and CRUs, the aircon, right, basically air conditioner, is not equipped for that density, right? It's like I can cool, let's say if it's a 10 megawatt data center, 10 megawatts in the entire data center. Now you're putting 10 megawatts in like a small part of the data center. That's challenging, right? So there's a lot of upgrades on that side, because a portion of the rack is still air cooled, right? And then, hey, if I don't have a solid water supply to there, my roof can't support it. Maybe instead of doing liquid cooling on the facility level, maybe I just stick it's called a sidecar, but it's effectively a massive radiator next to the GPU rack. So it's still air cooled, but the GPU rack itself is water cooled, and then it just connects to an air cooled rack of called a sidecar, which is basically just a massive radiator and fans, dissipating the heat into the environment. So there's all these things that people are doing to make data centers, quote unquote Blackwell ready. And once it's ready, it doesn't affect the performance or anything. It's just ugly and not as elegant, but that's fine, right? We deploy the GPUs, the user doesn't notice. And so when you talk about, hey, you have all of these, sidecars, you have, aggregated all the power together, great. Now what happens, next generation when power goes up again? Or it's a 5-year-old data center and you've retrofitted it for Blackwell, and 5 years from now or 6 years from now, you're going to now do, whatever's after Rubin or Feynman or whatever GPU generation, and it's higher power yet again. It turns out, it used to be you'd build a data center and there wouldn't really be much retrofit cost, right? You would slide servers in and out. You would rent racks to people. They'd come in and be like, oh, actually, I'm going to replace this one CPU server, but I'm going to keep my storage, or I'm going to replace the storage with SSDs instead of hard drives. And they'll go on with their day and they keep within the rack and it's fine. But nowadays, because the deployments are quite monolithic, right? You'll deploy massive chunks together, right? And users' contracts and the usefulness of GPUs will fall off altogether. You end up with, and then the power changes every time, the cooling changes every generation, right? From Hopper to Blackwell. And NVIDIA's already said what all the changes with Rubin, and it all changes again, power and cooling. You kind of end up with, between every GPU generation, there's actually a retrofit cost associated to the cluster. And that also has some pretty big implications for, what is the total cost of ownership of this cluster, of this data center? Hey, is my real estate on the data center actually a 30-year investment? Or is it really more like, hey, some parts of it are 30 years, some parts are actually 5 years?
Yeah. Yeah, it sounds like your prognosis is the so-called, like, let's say, like legacy data centers, like those that were built, let's say, a decade ago, they're still potentially valid for something like Blackwell, but probably not as cost optimal as newer generations of data centers. And it sounds like the other implication is newer generations of data centers, more than ability to accommodate Blackwell, it's really more about retrofitability. And that, like, if you're designed for these retrofits, it's like a little bit like where the airline industry wound up, right? Where like the plane lasts however long, but every so many years they're going to swap out all the seats and swap out the interior, and that's a little bit what the data center is turning into.
Yeah, it effectively, like, you're plugging in some retrofit time between each cluster. And you might not necessarily want to bolt everything down to the degree that you were thinking about before, right? Your UPSs and your switchgear and a lot of your networking stuff. Maybe you want to do something that is more modular, your power delivery, your cooling, et cetera, because you may have to change it again. And so some people have taken this to an extreme, right? Meta's got a data center design that's only built to last for a single generation, right? They put them in these like tent-like buildings, right? We call them tents because that's effectively what they are. Like, the closest thing you can think of them is like the building you go to when you go to like a local circus or fair, right? Mm-hmm. That's what they look like, because they slide in all the power equipment, they slide in all the cooling equipment and the GPUs, they wired it all together. And then after 5 years, they're like, well, I'm going to rip it all out and I'm going to put new stuff in. So why bolt it into the concrete? This is sort of one of their philosophies that they've sort of recently adopted over the last 6 months to, as they've really geared up into this meta super intelligence race, is because, why do I care? I just care about building it as fast as possible. Instead of necessarily, building a data center that's useful for 30 years and I can upgrade constantly over the next 30 years piecemeal, because that's not how AI systems work. Mm-hmm, mm-hmm. And this will cost upfront. It's going to cost less, right? Hey, if I'm not building a 30-year investment, I'm building a 5-year investment. It costs less, right?
Yeah.
Now, 5 years from now, I have to change it again, and then 5 years after that, I have to change it again. But their bet is sort of, hey, this increased time to market, this ability to modularize it and switch it all out faster and faster, will be less than having to retrofit this massive building that's concrete and steel that you have to drill into the concrete and all these other things for all the pieces of equipment that you thought were going to be permanent or 10 or 15 or 30-year installations, but in reality they're not. And so it's a lot like that airline analogy. I actually like that a lot, Charles, right? Because if you look down under your seat, below the flotation device is actually a bunch of bolts that you could. I mean, I have never tried. Maybe I should take a wrench and get kicked off of a Delta or United forever. But you could totally unscrew it and take the seat out.
Yeah, absolutely. Among other things. Yeah. This is super interesting. So jumping over to another kind of piece around architecture and workloads, and in the context of inference, which is kind of love your take on the state of specialization for AI compute. So I don't know, we probably go back 2-3 years where there was a lot of attention started to get paid to specialized semiconductor companies. There's a long list. I couldn't be able to enumerate them all, that are saying we're a specialized silicon that's just really excellent at inference. And there's more than one microarchitecture that's been designed for that. And they produce some very impressive benchmarks in terms of token throughput or other characteristics like this. But as you said, with Blackwell now we've got a pretty big jump in price performance compared to where we were. Do you think that shrinks or closes the window for specialized inference silicon? And kind of connected question, if you go all the way out to Rubin, there's actually a little bit of potential for specialization with Rubin for NVIDIA. And I'm curious what those two things, the existence of Blackwell and later on some of the unique optimizations you can do for Rubin, do you think that shrinks the window for specialized inference silicon, or do you think that they're going to coexist?
Yeah. So what's funny is we've always wanted to do specialized ASICs for the workload, right? So AI ASICs is sort of what everyone's talked about. There was for a long time it was oh, GPUs aren't specialized to AI enough, and then NVIDIA ripped every possibility of running graphics on AI GPUs, right? They have the regular GPUs that can run graphics. But GB200 cannot run any graphics, right? B200 can't run any graphics. So they've long and even Hopper was not good at it. So they've really ripped out all that stuff, and it is an AI ASIC. And then when we talk about, okay, in AI there's two workloads, right? There's training, inference, and for a long time, the goal was, hey, maybe inference has different workload use cases than training, but that ended up being a real big challenge, right? People ended up oh, we could fit the whole model on the chip. So for training, you do need all this external memory, but for inference, you don't. And then it turned out models just kept getting bigger and bigger and bigger and bigger, and so it wasn't possible, right? And even now, if models aren't really getting that much bigger, the use cases are in terms of, hey, how many users do I want to batch together? What's my context length, and therefore what's my KV cache, which means I need a lot more memory anyway. So it's kind of a real big challenge on that front as well. And so you've sort of had this evolution through, hey, I would love to have a specialization, but what does that specialization entail? And what's interesting is that, the exact opposite of what everyone thought was the case, right? Hey, inference is smaller chips, inference is, you don't need as much memory, and training, you need all that stuff. We're starting to see the opposite, right? And so if you're building a model up into a certain scale, it's actually more cost effective to use B200 for training, right? But it's almost always more cost effective to run GB200 for inference. And so you've sort of, which is the exact opposite of what you would have expected. Oh, use the big thing for training and use the small thing for inference. You've actually got the opposite, right? And so, you've got this weird role reversal, and that's because of the innovations that have been happening on the side of inference. And so when you look at specialized ASICs for inference, the same thing is happening, right? They're chaining dozens or hundreds of chips together, right? The DeepSeek implementation that's public by DeepSeek uses 160 GPUs, right? And so you look at these systems, it's oh, actually, I need this to be a pretty large system. Actually, I do need a lot of networking. I don't want to cut on networking cost. In
Yeah, I
fact,
was
maybe
going
I
to
care
say
more
these
about the
all these
networking.
yeah, these sparse MOE style models are pretty chatty and actually make pretty good use of the InfiniBand between the chips now too.
And they actually seem to get a bigger performance benefit from the NVLink than training does. Now, obviously,
Hmm.
training, so as we look to specialization, it's like, well, where are all the models headed? Well, they're headed to sparse MOEs, they're headed to super long context for agentic or reasoning tasks, and you end up with actually, if I want to serve a bunch of users, I need a really, really large domain of memory to utilize for KV cache and all the parameters because the models are huge too, and they're getting bigger too. You see this with Qwen 3 Max, right, as the newest sort of open source model that's bigger than their predecessors, which was the Qwen 2 family.
Hmm.
And so, and so, the models keep getting bigger, the KV cache keeps getting bigger, and so as we look to specialization for inference, NVIDIA's next generation actually has something very different. They're not saying, hey, there's a training GPU and an inference GPU, right? Because they're either's fine. What they're actually saying is in inference, we're going to split the workload into two things, right? We're going to split the workload into context processing, and we're going to split the workload into decode, right? Because when you look at Together AI's pricing on inference API or really anyone's, the way they charge is different, right? Hey, if I'm hitting an API from Together, my prompt is charged at a much lower token, right? All of those tokens to be processed is much lower versus the output tokens, right? Those are higher, and that's because of the nature of the workload, right? When I'm doing the processing of the prompt, it's called prefill. I can do everything in parallel, and I can process the entire prompt in maybe a second, 2 seconds, 3 seconds. It's fine for the user. But then when I'm talking about decode, well, actually, it's not parallel, right? It's actually very sequential. You have to autoregressively generate each token, through the model, which means you have to run through the whole model every single time for every token. And actually, a user is not going to find it acceptable for one pass through the model to take a second or 3 seconds. What they really require is, hey, it actually has to take 1/50th of a second or 1/100th of a second, i.e., 50 tokens a second, 100 tokens a second. That's what I need. And so the requirements are so different for decode versus prefill. And what's funny is training's requirements actually there's parts of it that fit to both. So you might not necessarily want to make a training chip because training is just going to want the biggest, fastest chip, and so does inference. But then what it wants in the biggest, fastest chip is on decode, you want a lot of memory bandwidth and capacity and networking bandwidth, whereas on prefill, you want a lot more compute. And so you've sort of like, well, training wants both of those things, but but on the inference side, both of these workloads are so vastly different. And so,
Hmm.
what NVIDIA's pitching is like a split of inference into two workloads, and we'll see if they're successful. There's a lot of challenges on the infrastructure side. Hey, when I buy my GPUs, I don't know what ratio my users are going to do it in. I don't know what my the next generation model is going to require on how many megabytes per token or bytes per token. What's going to go on with attention and how these attention mechanisms are evolving for long context. Hey, how long is the context going to be? People don't know. And so it's really hard to provision your hardware for something so specialized, such as a split ratio of decode versus prefill, day one, when you don't know in year two what's gonna happen to models and my user's workload. And so this is the challenge with over specializing. And the same applies to any ASIC that's just targeting inference as a whole, right? Hey, if I over specialize, what now happens with regards to, model architectures evolved this way? And so that's happened to a lot of these inference optimized chips, is they were imagining a world where it was large dense models, or it was small dense models then going to large dense models. And things keep changing, right? Models grow bigger than they expected. Models go sparse MOE. Models turn into this like wide EP, where you have to communicate a lot between nodes. Models turn into this thing where I have to actually ping, whether it's vector databases or MCPs, or I have to chain different models together. These things end up making the infrastructure challenges very difficult. In which case, do I really want to lock into something that's so specialized, or do I just want to buy the jack of all trades? Right, and then as the workloads evolve, well, I know my jack of all trades will continue to be, on the Pareto optimal.
Hmm. That's actually a good segue to another, like a related topic. So one of the things that we see it together is these AI native companies are um, in kind of the quest for more competitive advantage, they're trying to get more and more sophisticated with what they're building. And so we're seeing AI agent companies that are becoming model training companies, and we're seeing model training companies that are saying, "Oh, I need to actually serve the inference, not just train the model, and I need to provide like a more complete platform for how people build agents." So people are kind of like cross learning each other's practices, and we see like more and more organizations that are both model developers and also high volume inference users. I'm curious, when you think about those types of organizations, um, and the need to basically like balance these two workloads, what do you think the implications are in terms of how they chart out their infrastructure needs?
Yeah, so when it comes to these kind of users, they really don't they pivot so fast, right? There's a lot of these companies in AI, whether it's startups or even enterprises, right? You see them pivoting what they want to do rapidly. They're like, oh, I'm gonna fine tune a model for my use case. Okay, I'm gonna serve it. Oh no, serving reliably is actually really hard. Let me go find a model provider to help me inference. Or hey, actually I need to serve on my own. But training wise, I can actually go to someone who's going to provide a service for fine tuning. And so, but then that rationale can switch on an instant. It's like, oh, actually, I don't care about serving on prem. I can actually buy the inference stack from someone else or rent it
Mhm.
from someone else. And so you keep having everyone change because they're still trying to find their product market fit. They're trying to see what makes the most sense. And the good idea doesn't necessarily end up being the good idea. And so this is sort of where or the good idea ends up being, wow, I actually need a lot of engineering resources for this, right? And these resources are better served by working on where I can actually be competitive, not re-implementing something someone already else has, right? And so when you look through this sort of like microcosm, you have companies that were pre-training models that are like, I'm done pre-training, but I'm going to do a ton of reinforcement learning, right,
Right.
of open source models. Or hey, I inference models and now I'm actually going to start training them. Or hey, I'm again, like you mentioned, like I'm building agentic systems, but now I want to do reinforcement learning so I can, instead of just taking the open models, I can do something much more tailored to the data set I have. Or hey, I've got this software platform for offering code completions and things like that to the end user, right? Oh, all of a sudden I've gathered all this data. I bet I can train a model for some parts of the code pipeline that's cheaper and more cost effective and better than what I'm getting from a foundation model company, right? Or, oh no, the foundation model company is actually going after my business.
As
What do
well.
I do to defend it, right? So you have all these things, and so people are going to constantly be experimenting. Um, What's nice is for companies that try to be best of breed at just a couple things, there's a lot of room for partnerships. Also means some of their partners are going to step away because they want to try and do it in house. But there's a lot of room for partnerships, and their infrastructure needs are going to be actually quite varied. Um, and a lot of these founders, a lot of these enterprises are starting to recognize that they're going to pivot a lot, and therefore their infrastructure must be very flexible to this.
Yeah, yeah. Speaking of versatility, so semis analysis covers a lot of topics. Obviously, trends in the data center, trends in micro and systems architectures for all these next generation AI infrastructure. But you also follow or do a lot of research on the kind of next generation of clouds. Um, and I'm kind of curious, just from your point of view as CEO of Semis Analysis, why is that a research practice for you to begin with? Like, what do you see as the role of this next generation of clouds as part of this AI revolution? How do you, what part do you see them playing, and why do you think this is an important research practice for you?
Yeah, so the practice covering neoclouds, the TCO of data centers, the GPU rental markets, inference markets, all of these things is super, super important to us because I mean this is one of the most dynamic markets ever, right? You look at the performance and cost that Amazon gave in the general purpose CPU market, it was terrible, right? Amazon's margins are so high, and we see on these workloads, infrastructure cost is everything, right? And so there was clearly like, a need to step up and change things. And in a time of massive change, right? Hey, the database structures for general purpose CPU actually a lot of that stuff doesn't matter for data center AI GPUs, right? It doesn't matter for AI. Hey, these other things that this network that we've built for resiliency and reliability, actually it's really slow. And so this trade-off that I've made is actually really bad. And so there needed to be a different way of building the infrastructure out, and different clouds did it in different ways, right? And furthermore, so that cost structure was really bad, and there was a lot of legacy baggage, right? To this day, a lot of the big clouds have some legacy baggage in terms of what they're doing that actually harms AI performance, but it's an evolution of their technology that they already had and the teams that they already had that were focused on optimizing those things. And so because AI was so different, there came about a revolution for clean sheet designs. Hey, I'm going to implement hardware this way. I'm going to implement networking this way. Security and multi-tenancy is a very different thing. I actually don't split servers up. Services on top of them are very different and not part of your core competency, whether it's inference or training services. There's all these different aspects that were very relevant in the neocloud market. And at the end of the day, these hyperscalers also were negotiating massive discounts against the Intel and AMD and storage vendors of the world. Whereas now in this new age, especially 2023 to now, because NVIDIA is sold out of everything they have, the price is the same for everyone almost, right? And so you end up with this they don't get their economies of scale. Their software may be, not necessarily perfectly suited for the workload. And there's all these new services that need to be built on top, which they need to spin up teams for. Well, then newer agile clouds, i.e. what we've dubbed them, neoclouds, are the ones who can come and step up and actually do, offer this infrastructure service at better performance, better reliability, because the reliability practices are different between a general purpose cloud and an AI cloud, can offer better services on top, better cost, and security is, there's so many different, what are they going to do for the networking, which is different? What are they doing for lifecycle management, whether it be scaling, resource provisioning, automation, orchestration, right? Most people didn't want, a managed Kubernetes or managed Slurm offering before, but now that's really important. What are they doing for alerting you? Your storage, all these things were different in the neocloud space. And so new companies come about. Together is one of them, and they've really adopted and picked up, hey, TKC is something that, a hyperscaler is never going to offer, but it's something that Together offers. Or, hey, inference API services is something that Together offers. And to this day, while the hyperscalers now offer them, they might not necessarily have as good performance and SLA on them. And so, or hey, what's going on with reliability? Or hey, what's going on with networking? Hey, what's going on with all these different orchestration? Managed Kubernetes. Does Amazon offer that? And what does it take to set that up? Right? All of these things, new clouds can get to, and they can get to them faster and sooner. And so that's where we came about with hey, we want to research this industry. We want to be the go-to for research on this industry because, by the way, there's now over 100 neoclouds. Right? And the big clouds, and what's going on in pricing, what's going on in deployments and capacity and all these different things. And so we created this ranking system, Cluster Max, which goes through, numerous criteria that I've mentioned, as well as many others, 10 different major criteria, and each of those has major criteria within them, to review and rank and keep the cloud industry less opaque, because this is the largest spending decision you're going to make in AI is your infrastructure.
Super, super interesting. So one last question for you. Across everything we've talked about, one thing you could say about all of this is that there's just an incredible pace of innovation right now. The silicon architectures, the system architectures are changing. The data centers are retrofitting more and more frequently. The software optimizations that can happen in all kinds of different layers of the stack, and there's another generation of all these things that come every 6 months. It seems like. What's sort of the most, when you think about an organization that's charting out what their infrastructure plans are for the next 1, 2, 3 years, what do you think is the most suboptimal thing that you see, suboptimal mistake that you see teams making? What's the one piece of advice you leave somebody, whatever you do, don't do that?
I would say the suboptimal decision is that people aren't considering that their approach is just going to be wrong, right? Everyone has a thesis, everyone has an idea, and that's why they're trying to do it. Whether it be, hey, I want to do vector databases this way, or I want to have infrastructure built this way. These sorts of decisions. I want to do inference this way. Hey, actually, I think inference is going to be served in this way. My user base wants this. That's not, yes, it's good to have a very strong thesis and build as fast as you can towards one goal, but be ready to pivot and change it, right? And that's what I think is the biggest issue with most people's sort of infrastructure plans, their model plans, their serving plans. They hem themselves, they make a decision and they go slowly for it because they're afraid of being wrong, right? Or they go towards it and then they won't pivot, right? They won't change what they need to do. It's bad to say a company like Together AI has pivoted before, but you guys, your seed and Series A fundraising documents look very different than like what the business is today, and that's okay, right? That's what a good company does. It pivots. Amazon is not what Amazon was 30 years ago, right? Pivoting is important and doing it very fast and being able to, turn the nail and actually, actually ship what needs to be shipped and the customer needs, because no one knows what they need today, right? Everyone has ideas. So build it, and if that's not what they need, build something else, right? So be flexible and go fast, right? Because that's the only way you can actually capture a market and a moat in this crazy AI infrastructure and AI application race.
I like it. I think that's great advice to lead people with at the end of this session. I want to thank you again, Dylan Patel, CEO and founder of SemiAnalysis. Thank you for an excellent conversation.
Thank you so much. See you.